So in today's Mayo seminar, we will have the pleasure of listening to Arnab Bhattacharyya, who will tell us about total variation distance estimation being as easy as probabilistic inference. So without further ado, please, Arnab.
Okay, thank you, Jakob, for the invitation. It's a real pleasure. And I hope at some point I'll be able to visit you non-virtually. I mean, I've been looking forward for some time, but it hasn't happened yet. But yeah, I will at some point. Okay, thank you again. Yeah, and as Jakob mentioned, if there are questions at any point, please feel free to interrupt. I mean, we can make this as interactive as we want. I think, Jakob, you said, I mean, there's also time after the 1 hour, right? So, I mean, in case there's some intermittent discussion, I guess it's fine if it spills over a bit.
It's definitely, there's a lot of flexibility. We're at your disposal. You run the seminar and tell us about what you want to tell us about. Yes.
Okay. Okay, great. Okay, yeah. So thank you again. So my talk today is going to be about total variation distance estimation. And although it's about a very specific computational problem, I hope to convince you that there are a lot of interesting underlying problems, as well as a lot of other fundamental questions that one could address that have been relatively little explored in existing work. Okay. So I'm Arnab. I'm at the School of Computing in the National University of Singapore. And this is joint work with a bunch of people. So we meet actually every Wednesday, 10:30 p.m. Singapore time. And we have been meeting regularly for the last, I think, more than 2 years. I think it kept me sane during COVID. And and this is part of what we have been doing. We have also been, so mostly we discuss non-technical things, but this is part of what came out of those weekly meetings. Okay, so yeah, so we have Dimitrios Mirisiotis. He's currently a postdoc at NUS. He's also on the job markets. If you're looking for a fantastic candidate who works on computational problems about distributions and other large objects, then please feel free to reach out to him. There's Sutanu Gayan, who was previously a postdoc with me here, and now he's a faculty at IIT Kanpur. Kuldeep Meel, who is now a faculty at Toronto. He was at NUS previously. He's still at NUS. He has a joint appointment at Toronto. Vinod, who's at Nebraska, and Pawan, who is at Iowa State. Okay, all right. So the problem that we'll talk about relates to probabilistic models. So these are ways to represent probability distributions. And one could say that one of the holy grails of statistical machine learning is to be able to learn and to be able to do computations on probabilistic models that describe data generating distributions. Okay, so you have data that's being generated by a distribution that's kind of the de facto assumption in statistical machine learning. And one aspect of the question is to learn models for these distributions, and another aspect of this idea is to do inference on these models. Okay, so once you have learned the models, to be able to do computations on these models. And the work today is going to be about the second part, about inference. Okay. And there are different ways to represent probability distributions. So in this talk today, we'll be focused on probabilistic graphical models. So I'll specifically focus on directed graphical models, and I'll tell you a bunch of things about them. But one can consider also other graphical models like undirected Markov models, although we'll not talk about them too much today. Of course, there are other kinds of probabilistic models altogether other than graphical models, like deep generative models, which I know very little about, as well as probabilistic circuits, which are also a very general way to model probability distributions. And they include, as a special case, most of these probabilistic graphical models. Okay. And the algorithmic problem that we'll look at is the distance computation problem. So it can be phrased in this way. So suppose you have two descriptions. So suppose you have descriptions of two probability distributions. These are two probabilistic models, M1 and M2. And you want to know how close are the distributions that they define. Okay. So, I mean, like, even determining whether the distributions are equal or not could be non-trivial, because maybe you can have two very different representations of the same distribution. So they generate the same distribution, but the generating model look very much different in terms of the representation, and it can be a non-trivial problem to determine if they are generating the same distribution or not. Okay, so we'll be more concrete as we go on, but I hope the idea is clear at a high level. And more
Should we
generally,
think of, sorry,
yeah,
so
right,
just to have
yeah,
something in our heads, do we think
yeah,
about discrete distributions now, something like over the Boolean hypercube, or it could be
yeah.
anything?
Yeah, I mean, the problem as such as I'm stating right now could really be anything. But as you'll see, the kind of the way that we think about these questions in this work is we kind of try to look at the simplest possible setting in which these problems are non-trivial, and we try to study them there because I mean, like as I said, these questions are not very well studied. So in fact, we will be looking at distributions on just the Boolean hypercube. But in general, one can of course talk about these problems on other spaces as well.
Okay, and for the Boolean hypercube, the point is now also that the representations will be like way smaller than 2 to the n, something like that.
Right. Yeah. So as we'll see that for many, I mean, it can be easy to. Okay, maybe we'll come to that later. Yeah, I mean, but if the yeah, typically the way that these models are described are way smaller than the size of the space that they represent. So if you have so if you have n nodes and you are describing a distribution on an n-dimensional space, typically the size of the representation is kind of polynomial in n, the number of variables, and not 2 to the n or exponential in n, which is the size of the sample space. Is that clear?
Makes total
Okay.
sense.
Okay.
Thank you.
Yeah. Right. So, okay, so now so one can ask, of course, what kind of distance? There are many notions of distance or similarity measures between distributions. There's a class of similarity measures called F divergences, which include KL divergence, Hellinger distance, chi-squared. There are a class of similarity measures called Wasserstein distances, which are which are for probability distributions defined on a metric space. There's another class of measures called integral probability metrics. These are also defined with respect to a set of classifiers. But for this talk, as I said, I mean, our philosophy is going to be looking at the simplest, most fundamental problems and try to study them in as much precision as we can at the basic level. So we'll look at kind of one of the most basic notions of distances between two distributions, which is the total variation distance. So if you have two distributions P and Q over a common domain D, and for this definition, I'll assume that D is finite. As I said, I mean, we'll most often have D as just being the Boolean hypercube. So D is finite. So the total variation distance is defined as follows. So it's the maximum over any subset A over D. So any subset A of D of the absolute value of P of A minus Q of A. Okay, so it's the event which maximizes the absolute value difference between P of A and Q of A. Okay, and it's quite natural. It captures how well P and Q can be classified by an optimal binary classifier. The optimal binary classifier would just look at the event A, and that would maximally distinguish P and Q. It's theoretically well motivated. It's a true metric, satisfies the data processing inequality. So that's on one side, we can motivate total variation distance. But also, in contrast, I would like to say at the same time, I mean, the questions that we look at, I mean, the particular problem we look at here is for total variation distance. But really, one could consider the problem, the distance computation problem, for other notions of distances as well. And it's becomes very interesting to look at other notions, particularly if you have some application in mind. And I don't know of a systematic study of the computation of distances between probability distributions for other classes of distances as well, like KL divergence or earth mover distance or things like that. So I hope that like our work also motivates looking at the computational aspect of distance computation more generally for distance measures. Okay, but for the purposes of this talk, we'll be looking at total variation distance, which is fundamental in information theory and statistics. Okay, so for TV distance computation, well, the most naive algorithm that you could think of is just to enumerate over all the subsets A of the domain and to compute this difference. Okay, so that would even be exponential in the size of the domain. But one can quite easily get around that. I mean, so for TV distance, there's a nice equality that this is also equal to the L1 norm of the difference between the probability mass functions of P and Q. Okay, so this is just half of the summation over the points in the domain of absolute value of P of x minus Q of x. And this, obviously, the summation can be done in time, which is linear in the size of the domain. You just have to run through all the x's in the domain. But we will be looking at distributions on high dimensional spaces. So distributions on n variables, let's say distribution on 0, 1 to the n, the hypercube. So this distance computation would take exponential in n time if n is the dimensionality of the domain. So it's infeasible for these high dimensional domains, which will be of interest. So the question that we take up in this work is to understand for what classes of P and Q might this DTV computation be doable in polynomial in n time. Okay. Any questions right now? Or okay, I've turned off the video because it's kind of distracting. I mean, I'm not looking at the video because it's kind of distracting for me to look at my own face.
No, it's all. I think we're all fine at this point. Thank you so
Okay,
much.
sure. Okay, so we'll be looking at kind of one of the simplest possible setting that one can consider, product distributions. So product distributions are, you have these two distributions over 0, 1 to the n, and each consists of n independent flips of coins. Okay, these are not identically distributed. So you have P1 through Pn, which are where each Pi is the probability of the ith coin being heads, and similarly Q1 through Qn, which is the probability of the ith coin being heads in Q. Okay, so P generates an n-dimensional distribution, Q generates an n-dimensional distribution, and the question is to compute the TV distance between these two distributions. Okay, so at first glance, I mean, we were at the beginning we were thinking about TV distance more generally, and then we looked at product distribution, and it seemed kind of obvious to us that there should be some closed form solution, perhaps for the TV distance between P and Q. In fact, for example, if you want to look at the KL divergence between P and Q, the KL divergence is just the summation of the KL divergences between the marginals of P and Q on each coordinate. So summation of KL of Pi and Qi. Okay, so it can be trivially done in linear in n time. Yeah, so I mean, the intuition was that hopefully TV distance can also be computed efficiently. We'll see the story later on. Okay, and it's, as I said, I mean, it's one of the simplest possible n-dimensional probabilistic model you can consider. Typical algorithmic inference questions about product distributions are trivial. Like, for example, if I want to know the marginal on a subset of variables, I can quite easily just do it because the other variables which you are not considering don't matter. And the probability that a particular subset of variables equals an assignment is just the product of each variable taking on that value. So it's like product of some Pi or 1 minus Pi, depending on whether that coordinate is 1 or 0. So it's easy to compute the probability of this sample from P taking on some particular assignment. So inference questions typically are trivial for product distributions. We also more generally could consider Bayesian networks. So in product distributions, we have that that each variable is independent. Here you have some degree of dependency. So in particular, each variable depends on its parents. Okay. So the way that a Bayesian network is generated is that you first sample the roots, and then you condition on whatever you got samples, condition on whatever the samples you got for the roots. And depending on that, you sample the next layer, and you after that sample the next layer, and so on. So it's a directed acyclic graph on which this Bayesian network is defined. So there's a layering given by a topological order, and you can just sample according to that layering, and that eventually gives you a sampling of all the n variables. Okay, you can use that procedure to also write down the probability mass function. It's just the product of the conditional probability mass functions. So you look at each assignment to the parents of the variable, and conditioned on the parents assignment, you look at the probability that the ith variable takes on the value xi, and you take the product of all of them. Okay, so here the way the Bayesian network is specified is that for each variable, I have a description of what the variable's distribution is conditioned on its parents. Okay, so for each conditioning of its parents, you write down what the distribution of the variable is. Okay. All right. So in fact, any arbitrary probability distribution on n variables can be written in this way if the degree is allowed to be very large, because you can just simply factor using law of conditional. I mean, you can just factor p of x comma y as p of x times p of y given x and so on. But yeah, but if you require the in degree to be small, then each conditional probability distribution can be written in a compact way. Okay, so these are what Bayes nets are. So yeah, like generally the question is, if you have descriptions of two Bayes nets given in terms of the conditional probability distributions at each node, can we compute the total variation distance between them? And as we'll see, that exact computation becomes a challenge, and we'll often resort to approximation schemes. So we will look at relative approximation schemes. So relative approximation means that we are approximating the quantity of interest, here the TB distance, up to multiplicative error. So epsilon relative error means that I'm approximating the quantity of interest to within 1 over 1 plus epsilon and 1 plus epsilon multiplicative factor. Okay, so we look at both deterministic approximation schemes as well as randomized. Okay, so let me turn to the to our results. So first, we have kind of the surprising result. I mean, surprising for us at least, that for even for product distributions, exact computation of TB distance is sharply hard. So it's as hard as, I mean, it should be. Yeah, I guess it's super familiar to the audience in question here. Yeah, like so Sharpie hardness is as hard as counting the number of solutions to say a 3-sat formula. And exact computation of TB distance between two product distributions is as hard as Sharpie. In fact, it falls in Sharpie, so it's a Sharpie complete problem. Okay, so this rules out getting polynomial time algorithms even for product distributions. And we showed in this initial work, which established this Sharpie hardness, that it's actually possible to get around the hardness for in particular cases by allowing approximation. Okay, so for example, if P is the uniform distribution, so each bit is 0 or 1 with probability half each, then for any product distribution Q, we could approximate the distance between P and Q in polynomial time. This was via reduction to counting solutions to knapsack instances. Okay, so that was nice, but we left as an open question and a conjecture. Yeah, we conjectured that it is possible to actually approximate the TB distance between any two product distributions, and this was confirmed in a very beautiful work by Feng, Guo, Jerem, and Wang that I'll also discuss in today's talk. So they designed a randomized approximation scheme for estimating the TB distance between any pair of product distributions. Okay, so not just with one distribution being the uniform that was in our previous work, but for any pair of product distributions. In particular, this was their result that for any two product distributions P and Q, if they are on this n-dimensional hypercube, in fact, they have the result on an n-dimensional hypergrid, then epsilon relative error approximation is possible in order of n squared over epsilon squared time. Okay, so this resolved the question for product distributions, and it was quite interesting to kind of try to understand what actually is underlying the difficulty or easiness of computing TB distance. By the way, we had shown in this previous work also that if you look at arbitrary Bayesian networks, then even approximation is hard. In fact, even testing equivalence is hard. Knowing whether the TB distance is 0 or not, that is a hard problem if you look at degree 2 Bayesian networks. Okay, so in general, approximating should be a hard problem. And we wanted to understand, I mean, what about the graphical structure of the Bayesian network allows for approximation of TV distance in polynomial time. And what we showed in a more recent work is that there's a reduction from TV distance approximation to exact probabilistic inference. So probabilistic inference refers to the problem of computing the marginal of the probability distribution on a subset of variables. I'll define it more exactly later, but at a high level, morally, it means this. I mean, you're looking at a subset of variables, and I want to know what the probability distribution is on this subset. In general, for Bayesian networks, it has been known since the early 80s. It's a work of Cooper, I think, from 82, that even for a single variable, if you want to know what is the probability that that variable is equal to 0, that problem can be sharply hard. Okay. So knowing it exactly can be sharply hard. But by now, it has been well studied. I mean, there are classes of graphs for which probabilistic inference can be done in polynomial time. And our reduction gives a way to approximate the TV distance whenever whenever one can exactly do probabilistic inference. Okay? So in particular, if you have two Bayesian networks on n variables over the same DAG of bounded tree width, okay, then their distance, TV distance, can be approximated up to epsilon relative error in polynomial time. Okay, so right. Yeah, so I should not. So bounded tree width. So tree width usually refers to undirected graphs. So here I'm talking about a DAG of bounded tree width. So more precisely, what it means is we look at the tree width of the moralized DAG. So moralization is this procedure where for each variable and its parents, you put a clique. Okay, you substitute the directed edges from incoming into a variable with incoming into a node with clique on the node and its parents. Okay, so this results in an undirected graph, and if that graph has bounded tree width, then it has been well known for some time. Then you can do probabilistic inference exactly, meaning you can compute the marginal on a subset of nodes exactly, and then our reduction then enables efficient approximation of TV distance. Okay, maybe I'll just stop for a minute if there are questions.
Can you say anything or like, okay, so you have a DAG, you said, and I want to take tree width of that, so I just make a clique out of, but the DAG has not necessarily, well, it has bounded in degree to begin with, I guess. Otherwise, the tree
Yeah,
width
I mean,
will
if it
not be
is, yeah,
small.
then the problem is trivial because the representation size is itself exponential in n.
Okay.
So yeah.
But you're saying that somehow when you do this, when you replace predecessors together with the vertex with cliques, then somehow.
So for example, for trees,
Yes.
there's, I mean, undirected and directed are the same because you just have one node. So for trees, what I mean is if you have a DAG with each node having in degree at most one, so it's a arborescence. So then in that case, the undirected, the moralization results in the same graph, but undirected because there's no clique to put. So so basically for a tree, this our result will show that you can actually do efficient approximation of TV distance.
I guess, yeah, I guess the question is like this tree width measure can be very different from just taking the DAG and making all vertices undirected. Say a DAG with bounded fan-in, if I would just consider all vertices undirected and take that tree width, that might be a very different measure.
That would be a different measure, yeah. But I mean, actually, it's I mean, this notion is kind of natural because you can think of the probability distribution as having this factor structure, right? And each factor is a function of the node and its parents.
Yeah.
So you can think of it as like factorizing over these cliques. So it's somewhat natural to consider this moralization. So yeah, I mean, when you convert a directed model to an undirected model, you naturally get these cliques. And the tree width refers to the graph of refers to the undirected graph that you obtain after putting in these clicks.
Okay. Okay.
Okay. Yeah. Yeah. I should note, I mean, that this reduction is from yeah. So basically, the reduction is from TV distance approximation to exact probabilistic inference. It would be interesting to also do for approximate probabilistic inference, because in fact, the class of graphs for which one can do approximate, I mean, there are other, I mean, there are classes of graphs for which, I mean, we know how to do approximate probabilistic inference, but not exact. So this reduction actually does not work for when the inference oracle is approximate. So that is an interesting question. I'll come to other open questions later. Another open question is generally to consider distributions which have this kind of a factor. I mean, these look like, I mean, from your world, Jakob, I mean, they look like constraint satisfaction problems where you have a product of local functions. And one can consider, for example, sampling from the uniform distribution on satisfying assignments to a constraint satisfaction problem. So in that case, you would have, I mean, it would be proportional to product of indicator functions on these clauses. So we'll come back to these kinds of questions later on, maybe in the follow-up session, which is after the talk. But there are a bunch of interesting open questions relating to how one can extend the reduction that we have here, which is for the special case of directed graphical models, to more general undirected graphical models and to factor models. Other questions? Okay, then I guess I'll go ahead. Yeah. So in the rest of this talk, okay, let me first mention a little bit about previous work. So I mean, like for graphical models, I'm not really aware of previous work talking about distance computation, but people have previously looked at this question of the computational aspect of statistical distance more generally. So there was a series of kind of influential works by Goldreich, Sahai, and Vadan in the late 1900s, early 2000s, where they looked at TV distance computation for distributions that are samplable by Boolean circuits. Okay, so what this means is that you have a circuit. The inputs consist of uniform bits. So each bit is 0 or 1 with probability half each. And you look at the distribution that's induced on the output bits, okay, on the output bits. And what they showed is that this problem actually is a complete problem for several complexity classes of interest to the authors. In fact, they showed that their results imply that TV distance is hard to even additively estimate. So remember, we have been talking about multiplicative or relative approximation of TV distance, which is harder than the additive approximation. So in particular, if the TV distance is 0, multiplicative approximation would require you to output 0. But additive estimation could be okay with outputting something close to 0, right? So additive approximation is an easier problem, and even that is hard in general for sampleable distributions. Okay, so in particular, they said that they showed that it's a complete problem for the class of problem for SZK, so class of problems having statistical zero knowledge proofs, and even the specific question of estimating the distance to the uniform distribution is a complete problem for non-interactive zero knowledge proofs. So I won't go too much into this because, first of all, reasons of time. Secondly, reasons of my extent of knowledge about about these results. Okay. All right. So I should also mention that the additive approximation question for the graphical models that we have been considering is actually quite easy. So whenever you have a graphical model or any probabilistic model where you can sample and also you can evaluate the probability mass function at a point. Additive approximation becomes very easy. So because basically you can write the TV distance as an expectation over x in p of this quantity. Okay. And what you see, that what's inside the expectation, this is a bounded number between 0 and 1. So it's an expectation over x in p of this quantity, which is a bounded value. And if you can compute this q of x and p of x exactly, then Chernoff bound tells you that you can get a relative approximation of the expectation. Okay. So if you can compute q of x, so additive approximation is easy. So in particular, for example, for product distributions and Bayesian networks, generally from the representation, it's easy to compute this q of x and p of x simply by using the product representation, and so you can easily get an additive approximation of the TV distance. Okay. Yeah, so in the next portion of the talk, I guess in the remainder of this talk, I'll I'll kind of sketch the overview of the results that we have talked about so far, including the result by Feng, Guo, Jerome, and Wang. Okay, so first let's return to the hardness question, which showed that where we showed that between any two where we showed that the general problem of exactly computing the TV distance between two product distributions is sharply hard. So let's see why that is. Okay. And the reduction in retrospect is kind of standard. So what we do is we establish a reduction from a Sharp-P hard problem to our problem. And we use an intermediate problem, which we call a Sharp PMF equals. So what this problem is that you're given, okay, maybe first let me describe the Sharp-P hard problem. So it's a product version of the counting subset sum problem. Okay. So here you're given integers a1 through an and a target value t, and you want to find the number of subsets of a1 through an which multiply to t. Okay. So it's not very hard to show that this problem is Sharp-P hard. So now one can reduce this subset prod to this problem PMF equals. So PMF equals is a question about one product distribution. Remember, the TV distance question is about two product distributions. This is about one product distribution. So you're given the parameters of a product distribution and a value v, and you want to find the number of assignments which make the probability value be equal to v under that product distribution. Okay. So this first reduction from counting subset prod to counting PMF equals, this is actually a pretty straightforward reduction. I think it's a very nice homework problem when you're talking about these things. Yeah, I mean, if you're teaching a class relating to counting, I encourage you to give this as a straightforward homework problem. So the more interesting technical part is where we need to show this reduction from counting PMF equals to DTV. So let's see how that goes. So the idea is that, remember, I mean, we have one distribution P, and we are trying to count the number of x's which make P of x equal to V, right? So, so the idea is to define two pairs of distributions from P prime and Q prime, and P hat and Q hat, so that the difference between the TV distances between the two pairs is proportional to the count that we are looking for. Okay. This proportion here, the reduction involves this factor beta that I'll come to in just one or two slides. Okay. Just one remark: the fact that it's a difference of two TVs maybe gives a clue that the approximation question could have a different computational flavor than the exact computation problem, because if you think about it, I mean, even if you could approximate the TV distances between the TV distances up to a good relative error, because you have a difference, it's no longer true that you have a good relative approximation of the difference. So relative approximation of DTV would not give you relative approximation of count PMF equals, where the relative approximation of this counting PMF equals is also known to be hard. but this reduction that I'm telling you is not going to be able to show the hardness of approximating DTV between product distributions. And as we'll see, that is for good reason, because approximating is in fact in polynomial time. Okay. Okay. So let me just quickly sketch to you how this reduction comes about. So P prime and Q prime and P hat and Q hat are defined in relatively simple ways. I mean, so here I just show the reduction when this V is less than 2 to the minus n. There's a different reduction along the same lines, but a little bit more technical when V is more than 2 to the minus n. The basic idea is that, okay, you define so you use the fact that you can change the number of variables. So P is defined on n variables, on n bits, but I define P prime and Q prime on more number of bits. So like, for example, P hat, Q hat is on n plus 1 bits, where P hat basically copies P for the first n bits and sets P hat n plus 1 to 1, meaning that this ith bit is 1 with probability 1. And Q is uniform for the first n bits, and then the next bit is set according to the target value V. Okay, and it's actually quite straightforward to show that the TV distance involves a sum over the excess for which P of X is greater than V. Okay, and the next thing, P prime Q prime, what it will do is it will also involve the same sum plus a different quantity, which is proportional to the number of x's for which P of X equal V. And this, remember, is the counting problem that we wanted to solve, the count PMF equals. So if we can take the difference between TV of P at Q hat and TV of P prime Q prime, then basically you will be left with this term, which is proportional to the count. So you can get this clean. Okay. And I should mention here what is beta. So this beta depends on the granularity of precision. Okay, so here we use the fact that although these PIs and QIs are real numbers, they are specified up to some number of bits of precision, right? So if any PI is not exactly equal to QI, there's going to be a gap between them, which can be lower bounded by some quantity which is related to this beta. Okay, so this beta depends on the granularity of precision. It's exponential in inversely exponential in n potentially, but it's there, and we use that beta for designing the reduction. Okay. All right. Any questions?
I think
they're kind of
so far so good.
okay.
But,
Yeah, some interesting things about this reduction. So, for example, it seems like remarkably brittle. So, for example, I don't know how to show hardness to exactly computing TV distance to the uniform distribution. Okay, so if one of the two distributions is uniform, I actually don't know what the complexity status is for this question. Yeah, the reduction seems to be kind of sensitive to the exact choice of parameters for me. Okay. Okay, in case there are no questions, let me go on. So next, I'll say a little bit about the algorithm by
wait, actually, I did have a question. Did you tell us about
Sure.
the P prime thingy, or you explain it in any way, or we were just sorry, I missed it. Maybe
I don't want to go through the computation here, but like P prime and Q prime are defined in this way, which depends on the beta, this granularity of precision.
Yes.
And yeah, I mean, maybe if there's time after the talk, I can if you want, I can
So
go through
what
this.
happened? But there is basically up to there is one more bit, but the n plus 1 first bits, it's the same as the hat guys.
Yeah, n plus 1 guy is the same as the hat guys, and in n plus 2 they differ. Yeah.
Okay.
That's
And
right.
you're saying that basically now if we just and now if we just set up the calculation and do it carefully, then we get what you have at the bottom of the slide, and that's sort of that's it. That's what you can say.
Yeah. So this is the term which came from the hat, where you didn't have the n plus 2 bit, and you also get this additional term If you choose beta sufficiently small, depending on the granularity of precision, you get this term where which come from the contributions where P of X is exactly equal to V.
Okay, thanks.
Yeah. Okay. All right. So let's turn to the other question, on the flip side of the coin, how to approximate the TV distance. Okay. As I said, our first approach was based on a reduction to counting solutions to knapsack instances. And that actually results in a deterministic algorithm, which is also of interest, and that works when one of the two distributions is uniform, for instance. But we couldn't actually handle the case when P and Q are two arbitrary product distributions. And this very nice work by Feng et al. Boils down this question to a simple but quite clever Monte Carlo estimation problem. And it's based on a characterization of TV distance that I have not mentioned so far. That's in terms of couplings. Okay. Sorry. So let me just quickly recall for you what a coupling is. So if you have two distributions P and Q on a common domain, a coupling is a distribution on pairs x comma y such that the marginals are distributed according to P and Q respectively. So X is distributed as P and Y as Q. Okay. And an optimal coupling satisfies this condition that the probability that X is not equal to Y under this optimal coupling is the TV distance between P and Q. Right. So if you have an arbitrary coupling, it's not hard to show that the left-hand side is always at least the TV distance. Okay. And an optimal coupling can actually manage to make it be equal to the TV distance. So it's a dual characterization of TV distance in some sense. And in fact, we have a precise characterization of this dual solution. So if you have an optimal coupling O, then the diagonal probabilities, meaning the probability that x comma y equal to w comma w, that is equal to the min of P of w and Q of w. Okay. So in an optimal coupling, what happens is the probability of x comma y being the same is fixed. And then the probability of x comma y not being the same, you can just adjust to satisfy this constraint that the marginal of x is P and the marginal of y is Q. Yeah, I have a quick example here. Like, for example, if you have P and Q, which are two Bernoulli distributions, the TV distance is 1/3. So a trivial coupling is where you just take x and y independently. So there the probability is more than 1/3. But you can set up the coupling in such a way that the probability of x not is equal to y is exactly 1/3. And this is the optimal coupling. So in our case, we want to compute the TV distance between product distributions. So we'll naturally be interested in couplings between product distributions. And the hope is that some way, if we can get a hold on this coupling, then, and if we can compute probability of x naught under y, then we'll get a way to also compute the TV distance in this using this nice dual characterization. So how do we get a coupling between product distributions? Well, I mean, a very natural idea is to consider the coupling between two product distributions as being a product of the couplings. Okay, so if you can couple each Pi and Qi, and I can define C to be the product of these couplings, then you can see that it's actually also going to be a coupling of the two global distributions, because each coordinate is going to be a copy of the respective coordinate of P. Like, let's say if I look at the first coordinate of O1, it's going to be a copy of x1. First coordinate of O2 is going to be a copy of x2, and so on. And these are independent. So the first coordinate of the OIs altogether is a copy of x, and the second coordinate of the OIs altogether is a copy of y. So this gives you a coupling between the two global distributions. And I mean, it may seem that the coupling, optimal coupling, should also be this kind of a local coupling. Unfortunately, that's not true. I mean, if it was, then we could be done much more easily. And in fact, actually, I mean, for most examples that you can come up with, the local coupling is not optimal. Okay. Nevertheless, I mean, there's maybe, is it true that in some sense, like a local coupling is close to being optimal? And this was the very nice observation by Feng et al., who showed that I mean, the probability of X not under Y for the optimal coupling, this is exactly the TV distance. Okay, so this is, as I said, so this is what optimality means, that this is the TV distance. And now if you have the local coupling, this probability is going to be more, but it's not going to be too much more. Okay, so they showed that it's going to be at most n times more. Okay, and the reason is actually very simple to show for these product distributions, because the probability of X not equal to Y is at least the max, is at least the TV distance between one of the marginals. Okay, so it's at least the max TV between any of the marginals. And the denominator is at most the probability of Xi not equal to Yi just by the union bound. And because Xi not equal to Yi is the TV distance between Pi and Qi, because I've coupled each coordinate individually, optimally. So the probability of Xi not equal to Yi is the TV distance between Pi and Qi. So this ratio just becomes the ratio between max and sum, which is at least 1 over n. Okay, so now it turns out that we can now compute with this local coupling is in some sense not as bad. And for the local coupling, the probability of X not equal to Y is quite easy to compute, because probability of X not equal to Y is 1 minus the probability of X equal to Y. And the probability of X equal to Y, I know how to do what is the probability of X equal to Y equal to W, right? Because I can just, I know what is the probability of Xi equal to Yi, because it is exactly the mean. As I said, I mean, there's a characterization of the diagonal probabilities. So probability of X equal to Y, you can easily compute in this way. And so probability of X not equal to Y for the local coupling, you can easily compute. So it means that for this ratio, we can easily compute the denominator. So if we could only compute this ratio, which is guaranteed to be not too small, then I could multiply this ratio with the denominator and get the numerator, which is what we want. Okay, and this is what is the goal, is to compute this ratio alpha, which is this ratio between the probabilities of X not equal to Y under the two couplings. And yeah, so here, okay, so I guess I can go, yeah, I don't know how slow we want to go. I mean, maybe I can just go through, I can just describe at a very high level now, and then later if there's interest, we can kind of dive into it and see what is actually going on. So you can define, so again, going back to this, we want to define an estimator for this ratio, which we know is not going to be too small. It's going to be at least 1 over n. Okay. So the way they do it is that we can set up two functions, f and g, okay, in such a way that alpha is the ratio of the sum of f of w divided by the sum of g of w. Okay. And we want to get an expectation of this, we want to get an approximation of the ratio of these two sums. Okay. And there's a very classical idea, like how to get the ratio, how to estimate the ratio of two sums, which is that you can look at the expectation of f of w over g of w with respect to a distribution pi, which is proportional to g. Okay, so if I write down this, what is x? So pi is g of w divided by the sum over w of g of w. So that is the probability distribution which is proportional to g of w. So the expectation over pi of this ratio is going to be exactly the sum of f of w over the sum of g of w. Okay, so it turns out that we just have to compute this expectation, right? Alpha is this expectation. And this naturally leads to this idea of using a Monte Carlo estimate for this expectation. So if I could evaluate, so if this f of w over g of w is bounded, and I can make samples from pi, then I can actually approximate this expectation, get a relative approximation of this expectation by just taking a Monte Carlo average of f of w over g of w for some polynomially many samples from pi. Okay, so and then sampling from pi. So pi is this distribution which is proportional to g, and there's this very nice connection between sampling and counting. So sampling from this distribution which is proportional to g is can basically reduce to computing the sum over W G of W. Okay. And this is again this probability of X not equal to Y under the local coupling, which I argued is easy to compute. Okay. So in fact, you can sample from this pi efficiently, and sampling from the pi allows you to then get a relative approximation of F of W over G of W. Okay, if there's interest after the talk, we can go through this in more detail. Okay. All right. Is there any immediate question someone wants to ask? That will give me a chance to elaborate. Or otherwise, we can just keep it to after the talk.
Seems like we should move on at this point, maybe.
Okay, sure. So let me finally talk about the work which appeared in the title of this talk, where we reduce from TV distance computation to inference. Okay, so what exactly I mean by inference is actually this. So the TV distance between base nets P and Q on DAG G can be approximated up to epsilon relative error in time, which is polynomial in n over epsilon squared, if for any G structured base net R. So if you have, so P and Q are on G. So if it's true that for any base net which is on G, one can efficiently compute R of S for any product set S, then you have this polynomial time computation. Okay. So what a product set S means is that I assign values to each variable. So for each variable, I say that variable is in some set, and I take so I assert that individually for each of the coordinates.
So sorry, a very near question. R of S is, what is this quantity that we're computing?
So,
very basic
yeah,
question.
so I'm saying that if it is true that for any base net on the same DAG G, one can compute the probability on product set. So what a product set is, it's a generalization of, so initially in the introduction, I said that one should be able to compute marginals on a subset of variables. So marginal is a particular example of a product set where for the variables in question, you have exact values. So let's say I want to know what is the probability of x1, x2, x3 being equal to 1, 1, 1, right? So for variables 1, 2, 3, I have the values 1, 1, 1. And for the other n minus 3 variables, I allow them to be 0 or 1, 0 or 1, 0 or 1 separately, right? So the product set in question is 1 cross 1 cross 1 cross 0, 1 cross 0, 1 cross 0, 1, etc. Okay? Does it make sense?
Oh, so you're saying that the structure G is fixed. I impose a base net R, and then I say, oh, now I'm interested in the product set, x1 being true, x2 being false, x3 also being true with the other variables, whatever, and I'm looking at the probability mass of this outcome.
Right. And actually, so
and you want to be able to compute that quantity exactly.
Exactly. Yeah. And actually, even though P and Q are on binary variables, this R, in our reduction, the R actually will not be binary. So, even though these are on alphabet 2, this R will be on alphabet size 4. Okay. So these will, as we'll see, it will consist of pairs of variables instead of one variable. So like R is on a larger domain than what so the variables of R are on a larger domain than the variables of P and Q. Yeah, but we still want this property that for any product set S, one should be able to compute the probability efficiently. Okay. And this property is is well explored in the literature on graphical models. So for example, we know that obviously for product distributions this is true. For trees and bounded tree width, there's this there's the the sum product theorem, I mean, like, which allows you to compute these in polynomial time. Yeah, this is also called the variable elimination algorithm. So there are so this bounded treewidth is a is a very large class of graphs for which one can assert this, that any product set probability can actually be the mass on any product set can be computed exactly in polynomial time. Okay, and the reduction is from TV distance approximation to exact product set. Sorry, yeah. I mean, like, yeah. If you have exact inference oracle for in this sense, then one can approximate the base net. One can approximate the TV distance in polynomial time. Okay. Okay, let me just give a very quick overview, I guess, because I mean, we're at the 1 hour mark. So the idea is to do something very similar to what was done for product distributions, and to again look at the optimal coupling, and then if we can get a local coupling which is close to being optimal. Okay, but here one runs into issues. The main issue being that it's not so straightforward anymore to design a global coupling which is also local in some sense. Okay, in fact, we don't know any way to do it. I mean, a coupling which is global, and then also it also respects the fact that each copy of X and each copy of Y should, I mean, like, each copy of the first and second variable should look like copies of X and Y, or should look like copies of P and Q respectively. Okay. So what we do, in fact, is we work with something that we call a partial coupling. Okay. So what a partial coupling means is that, partial coupling is in fact okay, so let me go through this definition a little bit slowly. So if I have two G-structured base nets, P and Q, what we mean by this locally optimal partial coupling is that it's also another G-structured base net. Okay, again, reminiscent of the sense in which we looked at this local coupling as also being a product distribution. Okay, so we were coupling two product distributions, and the coupling itself was a product distribution. Similarly, here also we'll insist that if the two P and Q have the structure G, then the coupling itself also have the structure G. But now the coupling is on these pairs x1 comma y1 to xn comma yn. Okay, so this is what I was saying, that even if the initial distributions were on binary variables, now this coupling is a base net on pairs of binary variables. Okay, so they're on, now they're on alphabet size 4. Okay, and we want these properties. So we want that if I look at the copy of the x size, okay, this is 1/2 of each pair on each node, then x size should form a copy of P. Okay, and also it should be true that it should be kind of optimal coupling locally, in the sense that the diagonal probability, so the probability that xi equal to yi equal to b, okay, so probability that xi comma yi is equal to b comma b, conditioned on anything for its parents, is equal to the minimum of the probability of xi equal to b conditioned on x's parents being c1, and probability of yi being b conditioned on yi's parents being c2. Okay. Okay. All right. So this is the main thing to emphasize here is that we only insist that one side be a copy of P, and the Y's need not be a copy of Q. Okay. In fact, we don't know of a way to insist that both be a copy of P and Q separately, and then at the same time they satisfy this optimality condition. Okay. So if this is true, then in fact we can show that again. You can define this f of w and g of w to be an estimator. So the sum over w, f of w over sum of over w, g of w, to be an estimator of the ratio between the probability of x not equal to y in the optimal coupling versus x not equal to y in this other joint distribution, which is actually not a coupling. Okay. and then one can again get a Monte Carlo estimate for this. But then kind of crucially, in order to solve the sampling problem, so you remember in the earlier question, we had to sample from pi. And then also in order to compute this x not equal to y under this locally optimal partial coupling, okay, not an exact coupling, we need access to an inference oracle, okay? And this inference oracle is what is allowed by our by the condition of the reduction. So if one has this access to, so if for the coupling distribution, one can compute product set probabilities efficiently, then in fact, one can compute probability of x not equal to y efficiently, and one can also do the sampling problem, solve the sampling problem efficiently, and this allows estimation of this ratio, which is in turn exactly equal to the TV distance. Okay. Yeah, I'm sorry if this last part was a bit rushed. I'll be more than happy to go through it in the next part of the session. But let me conclude here. So first of all, one interesting question is that we have upper bounds now in terms of the tree width of this DAG. It's not clear. I mean, tree width is actually known to be the right characterization for inference. So, like if I want to look at the marginal probabilities, there are parametric lower bounds in terms of tree width, fine-grained parametric lower bounds in terms of the tree width for the inference problems. We don't know if tree width is similarly the right notion of tractability for TV distance computation. I think this is a fascinating open question. Another class of problems is, I mean, like another class of questions is for TV distance between other classes of probabilistic models. As I mentioned earlier, as I alluded to earlier, we've been looking at Bayesian networks, but one can ask similar questions about any class of product or any class of probability distributions that factor in some structured way. Okay, and for these kind of factor models, can we develop more general classes of algorithms for computing distance? And as I mentioned, I mean, there are some interesting connections to sampling and counting solutions to constraint satisfaction problems that I can mention later. Another question is, what about other notions of distance or similarity between probabilistic models? So here we looked at the TV distance, but one can also look at KL divergence. So for KL divergence, it's kind of interesting. As I mentioned, for product distribution, KL divergence is super easy. Just add up the KL divergence between the marginals. For Bayesnet, something interesting happens. I mean, again, if the Bayesnet has bounded tree width, then we know that we can exactly compute the KL divergence. If the tree width is not bounded, we actually don't know. I mean, maybe what the status of the problem is computationally. Does it become hard? Is there still an efficient algorithm either to compute it still exactly or even to do it approximately? We don't know. And one can go beyond TV and KL to consider other notions of distances like Earth mover distance, which are maybe more relevant for distributions over real valued spaces, and other more complicated notions of similarity metrics. Okay, so I'll conclude here, and as I said, I'll be more than happy to answer questions, and I guess I'll be here available for the next hour to discuss in more detail some aspects of what we just talked about. Thank you for your attention.
Thank you so much, Arnab. One question which you touched upon. So, do you believe that this should still be sharp P hard if one of the distributions is the uniform one? Like that was open, right? And
Yeah,
it was sort of.
Yeah, so if one of the distributions is uniform, as I said, I mean, there's a way to easily get a approximation algorithm via counting solutions to knapsack. I mean, counting solutions to a knapsack instance. But I mean, yeah, but of course now there's also more general approximation algorithm between any pair of product distributions. We don't know for the exact problem. Yeah, I don't have a guess really about what the status is. I mean, yeah, I would not put any money either way. Yeah.
Fair enough. And you probably said this, but where was, because this, for if one of them was the uniform distribution, you had a deterministic algorithm, right?
Yeah, yeah.
But here, so remind us, like here, you in the general case, you needed randomness.
Yeah, so that's also a good point. Yeah, so here I think when I prepared the slides, there was only a randomized algorithm, but more recently there's been a recent work which gives also a deterministic algorithm for this question between product distributions. And I suspect, I haven't really looked at it. I mean, like our work is independent of that work. I mean, so it may be that we can combine the ideas from that work and like what we did for bounded treewidth Bayesian networks in order to get a deterministic algorithm for bounded treewidth Bayesian networks. But I haven't looked at that problem, to be fair. Yeah.
I see. No, I was just trying to see if I could remember, like, where in your algorithm did the randomness show up.
So so here the randomness shows up because you ultimately do you sample from this distribution pi, and you do a Monte Carlo average of this f of w over g of w.
Oh, yeah, right. Yes. Okay.
Yeah.
Yes.
So that is, that's exactly where it shows up.
I see. Let's see. Is there any other question from the audience before we take a break? So then maybe let's just thank you again, Arnab, for this presentation. So we're back after the break, and for as you can see already on the screens, that there's the setup is for a more technical talk, and it suggests that Arnab will explain more to us about couplings and how they go into the proofs. So without further ado, Arnab, the floor is again yours.
Okay, thank you again, Jakob. So let me first just give some general background about couplings and their relations to total variation distance. So suppose you have two, so we are not going to talk about product distributions right now. So very generally, if you have two distributions, right? So if you have P and Q are two distributions. So please tell me if my handwriting starts becoming illegible.
I'm very envious at the quality of your handwriting. So my students would cry with joy if they saw this. But they don't.
So we can define a coupling as so let's say x comma y is a coupling of P and Q. Simply, I mean, what a coupling simply requires is that x is a copy of P, so x is distributed as P, and y is distributed as Q. Okay, but x and y are coupled, so they're I mean, there's a joint distribution on x comma y. Okay, and I mean, it's clear that, I mean, one way to do a coupling is just to do independent copy of P and independent copy of Q, right? And so maybe let me make this first claim. For any coupling xy of P and Q, you have that the probability that x not equal to y is at least the TV distance between P and Q. Okay. And as I mentioned earlier, so there is an optimal coupling, which is mostly never the trivial coupling, which actually makes this at least an equality. Okay. And let me go through the proof of this. Okay. Okay. So so let me call I don't know, let C be the distribution, I mean the coupling distribution on x comma 1. So x comma y is the random variable which describes a sample from C. Okay. So one thing that we know is that for any, okay, so what we know? So we know that for any x, right, it should be the case that sum over y of C of xy should be equal to P of x, right? This is just from the fact that we want the marginal of x to be distributed as in P.
Mm-hmm.
Does that make sense?
Yes.
Yeah. So I mean, so if I just sum over all the possibilities of y, so the probability of x as being the first coordinate should be P of x. So this means that C of x, so C of x in particular should be at most P of x, right? Because it's one term in this sum of non-negative values, right?
Yes.
And similarly, C of xx is smaller than Q of x. So which implies that C of xx is at most the min of P of x and Q of x, right? Right?
So you probably said this already, but P and
Yeah,
Q, they're living over this, they're living on the same domain. This is
yeah, P and Q are on the same domain. Yeah.
Mhm.
Okay. So good. So now what we can say is that yeah, so now we want to look at what? Probability of x not equal to y. So I want to relate that to TV. So I'm just going to use this property. So what is the probability of x not equal to y? Well, it's 1 minus the probability that x equal to y. And what is the probability that x equal to y? So it's basically sum over all the possible little x of C of x comma x, right? Right. And by just what we just established, this is at least 1 minus sum over x of min of P of x and Q of x, which is, yeah, so another way to write this is that sum over x of P of x minus min of P of x, Q of x. So here I'm using the fact that the sum of P of x is equal to 1.
Mhm.
Okay. And here, if you look at this, what is this expression? So basically, you can, yeah, you can partition this sum into two parts where P of x is bigger than Q of x and when P of x is smaller than Q of x. So when P of x is smaller than Q of x, then basically this term is equal to 0 because it's P of x minus P of x. And when P of x is bigger than Q of x, then this is P of x minus Q of x. So this is like sum over x. Maybe I'll write it this way. So you can write this as sum over x of max of 0 P of x minus Q of x.
Mhm.
And this is actually exactly the TV distance between P and Q. Um,
And
yeah, so
now
this is
another very naive question is like,
yeah,
because the stupid coupling would be to set, I guess, like x to p and
yeah,
y to q, and that
yeah.
would not achieve this total
That would not,
variation bound.
yeah, that would not achieve this total variation bound. Yeah. Um, yeah. I can show that slide with the simple example, which
Yes.
let me do that. Yeah. So the other claim, which we'll get to, is that there actually exists a coupling, and this is maybe somewhat surprising, that actually achieves this, that actually makes this inequality tight.
Okay.
Where was it? Yeah. So yeah, so here, for example, P is 1 with probability 2/3 and 0 with probability 1/3, and Q is 1 with probability 1/3 and Q with and 0 with probability 2/3. So the TV between P and Q is 1/3, because if you look at the probability of 1, it's 2/3 in P and 1/3 in Q. So that the difference is 1/3. So
And
TV
just
of
to
PQ is
again, just a very basic. So a coupling, it's
Mm.
really a distribution on distributions, right?
No, it's a distribution on pairs. It's not a distribution, it's a distribution, it's a pair of random variables which are correlated.
Yeah,
So
but well,
for
it's a
example,
yes. Okay,
so
yes.
so it's one particular pair distribution on pairs. So one pair, one possible coupling could just be to sample X from P and Y from Q. So it's a product of P and Q, basically. So in that case, what is the probability that X is not equal to Y? Well, this is the 1-0 probability that that X is equal to 1, Y is equal to 0. And then there's the 0-1 probability that X is 0, Y is 1. So this is 5/9. So this is bigger than the 1/3, right? So
Okay,
I mean, this is showing that.
let me go really basic here. So
Sure,
just to
sure.
see if I'm completely wrong direction or if I'm following. So the point
Yeah.
is, if P and Q happen to be, let's see now. Oh no, I thought I had it. So
Mm.
P and Q are distributed on a common domain, but are they somehow correlated
Oh,
or
so
not
P and Q
really?
are two different distributions.
They're
So
completely
the
two different.
coupling, they're two different distributions, and we are trying to compute the TV distance between the two distributions,
Yes.
considered separately, right? But this coupling is a distribution on pairs, so that, I mean, the basic idea is, I mean, the word coupling comes from the fact that you want to make X and Y be equal as much as possible, but still have the property that X, just if you look at X separately, it's distributed as P, and Y separately is distributed as Q. So here, I mean, you're not coupling X and Y. So you're taking X and Y to be independent copies of P and Q respectively. And there is probability that P X is not equal to Y. So another example of a coupling is that, let's say
But
I
for
take
instance, like if P and Q were both just uniform distributions,
Mm.
completely uniformly random,
So then the TV distance
then
is 0,
they're
right? So the TV
oh
distance is 0. So one way to get this optimal coupling is just to make Y equal to X. So you sample X randomly and you set Y to be the same as X,
oh
right? So in this case, if I look at each coordinate separately, it's uniform, but then they're coupled together because they're always equal. So probability of X not equal to Y is 0, and which actually matches the TV distance,
I see, I
right?
see.
So the game is, how do you construct this joint distribution so that the marginal behaves like P and Q, but they have higher probability of, they have as much probability as possible of being equal.
Okay, I'm slowly getting a more of a feeling for this. Okay, great. And now
So
you
for
have your
example, like kind
example.
of an anti-coupling is where, let's say I take X sample from P and Y
Mm,
as just being 1 minus X, right? So in this case also, X is obviously marginal is P, Y's marginal is Q, because 1 minus something which has probability 2/3 of being 1 has probability 1/3 of being 1.
mm-hmm.
So Y is sampled as Q, but then X and Y are never equal. So this is even worse in the sense that the probability of X not equal to Y is even higher than 5/9. And the
Mm-hmm.
optimal coupling looks kind of artificial, but as we'll see, there's another way to view it which makes, I mean, yes, I mean, so there's a different way to characterize an optimal coupling. But if you take X as sample from P and Y as this kind of weird distribution, it's a uniform, it's a random bit of X is equal to 1 and Y is 0 otherwise, then you can check that Y's distribution is the distribution of Q.
Mm-hmm.
But what is the probability of X
But
not
it
equal
stands
to
to
Y?
reason because y has to be 0 more often. So we sample X, and if X is oh P, I mean if X is 0, then Y definitely has to be 0.
Mm,
Uh,
yeah. So
but
yeah, I'm
but
putting
if
high
but if
mass.
it, yeah.
Exactly. Yeah. So there's the only way that they can be different is if X is 1,
Mm-hmm.
right? And if X is uh and X is 1 with probability 2/3. And then the probability of Y being 0 is half, because I just flip a random coin if X equal to 1. So the probability of X not equal to Y is 1/3 in this case. And that turns out to be the absolute minimum you can make this probability
And we're going to use this
for
for
exactness.
somehow, we want to sample in a correlated way, but still with correct marginals. Is that the way to think about
Exactly.
it?
Exactly. Yeah, exactly.
Okay. Mm-hmm. Perfect.
Okay. So now let me get back to the notes. Is there a comment? I see like another in the chat, but
You are audible. We can hear you. Yeah, no, I
okay.
think
I think I wrote
this
that.
was from
Okay.
earlier.
Okay.
This is when I was struggling
Okay.
with my headset. Mm-hmm.
Okay. So now let me write claim 2, that there exists a coupling of P and Q such that probability of X not equal to Y in this coupling is actually equal to the TV distance between P and Q. Okay. And yeah, this is, I'll just construct one, and then I'll
Mm-hmm.
argue that this is a coupling. Okay. I
Mm-hmm.
mean, the motivation comes from here. I mean, like in the proof, we saw that C of XX is at most min of P of X and Q of X, right? So we saw here that C of XX is at most min of P of X and Q of X for any coupling. So now we'll just insist that, so define, oh, I don't know what to, oops, some lag, such that, uh, yeah, C of XX equal to min of P of X and Q of X. Okay. And so these are the diagonal entries. And then I also have to specify the non-diagonal entries. And I'll specify them in such a way so that I satisfy this property that the first half is a copy of X, copy of P, and the second half is a copy of Q. Okay, so these are diagonal entries, and then the off diagonal entries. So for off diagonal. Let's say X comma Y, I'll do C of X comma Y is equal to P of X minus C of XX times Q of Y minus C of YY divided by 1 minus sum over X, C of XX. I hope I got this right.
So again, we want. I'm just sorry for being slow, but it's Friday
Sure,
afternoon and everything.
yeah, no problem.
Yeah,
Yeah,
I think I'm finally getting this. So I mean, we want
okay.
to have it like these I think of this as this somehow two-dimensional. We have some space S, and now we're constructing a distribution over S squared. So
Right,
again, we just do the marginals on the rows and the columns. These are numbers, and we know that
right,
they sum up to 1. And
right,
now we sort of want to construct a distribution on this whole square matrix, maximizing the weight of the diagonal, right?
right. Yes, exactly.
And since it's non-negative, you're just saying, well, if we're looking at row, the diagonal element number 5, clearly you cannot go over the number in row 5 or the number in column 5. So you'll just basically go, and it's not obvious that you could even attain these numbers a priori, maybe,
Exactly.
but
Yeah.
optimistically, let's shoot for the stars.
Right.
Okay, so you fill in that, and then miraculously it turns out that you can get the rest of it to work.
Yes. Yeah.
By your magic formula that I will now look at.
Yeah.
Is there a way to understand what this is? Sorry.
So basically, what we are trying to ensure is just that the copy of X, like the sum over XY, C of XY is equal to P of X. This inequality, and the same thing for Y. So we want to get both of these to be true, right? So that will ensure that this is actually a valid coupling. And then after that, the fact that it's actually equal to the TV distance just comes from the fact that, in this computation, there was exactly one inequality right here. So if this becomes an equality, then the whole thing becomes an equality.
Good point.
So I just need to ensure that this is a valid coupling, and that's it. Right? And do we want to do that? We can. Let's just do it for one side, and then we'll leave the other side. So if I want to look at, so what do I want? So I want to look at a sum over y of c of xy, right? So okay. And also I need to ensure that this is non-negative and they add up to 1. This is a valid probability distribution. So first of all, non-negativity should be clear because each C of XX is smaller than P of X and C of YY is smaller than Q of Y. So the numerator is positive. So this is positive, right? So this is non-negative. So that should be clear. Let's check. Maybe let's check that that it's properly normalized, that the sum is 1. Um, yeah, actually, okay, so maybe I think I should make this Z because this is a different X than these. Let's remember some equals Z. C of Z equals Z. Okay. Um, right. So let's check if this is a, so let's do sum over xy of C of xy. So we have these two. So if it's diagonal, so we can do sum over x C of xx plus x not equal to y C of x comma y, right?
Mhm.
Um, and the first is just sum over x of min of p of x, and maybe I'll get myself a little bit more space. Okay, so this is equal to sum over x of min of p of x and q of x. And then the other x not equal to y. Yeah, okay. Actually, Jakub, do you really want to go through this? I think it's
No, I think it's
standard.
yeah, I don't know. I mean, I sort
Yeah,
of get the you need to calculate. I mean,
yeah. So
it's
basically,
I mean,
you
something is happening,
establish.
but you have the denominator. Oh, so let's see. I know the
Oh, sorry.
denominator is sort of the remaining weight that you have to distribute once you're done
Exactly.
with the diagonals. So you need to
Exactly.
somehow normalize by that,
Yeah.
and then the numerator, I'm not so sure, but it's sort of you're saying that somehow this is more or less you write down, if I think about it long enough, then I'd realize that, okay, I'd better do something like this or else I'm screwed, and you write it down and it
Yeah.
works.
So right. So basically, you ensure these three things that one, that the sum over xy of C of xy equal to 1.
Yes.
Then for all x, for all x, sum over y of C of xy is equal to P of x. And then the
And
other way around
subject to
also.
this, you maximize,
Yeah.
and subject to non-negativity. I mean,
Yes. Yeah. And also non-neutral. Y. And also each of these is, yeah, non-negative. Yeah. And C of xy.
so you're basically, I mean, we're basically, right, we're solving some kind of LP, are we? I mean,
Yeah. Yeah. I mean, right. So, and the probability of x not equal to y is 1 minus the probability of x equal to, yeah. And so basically, we say, so probability of x not equal to y again is 1 minus the probability of x equal to y, which is sum over w of c of w comma w. Or I was
and do
using
we
x.
care about the complexity of this guy? Does it come in anywhere in the analysis or not really? I mean, like it seems like, yeah, I just continue saying naive things, but
Yeah, no, no, it's fine.
it seems like, is it true that if P and Q were not too complicated, then somehow C is also not too complex?
It's a very good question. And that's kind of like essentially the heart of the problem we are looking at, right? I mean, like this
Oh,
optimal coupling. If we had a way to kind of do computations on it, like if we had a good handle on it, then
mhm.
presumably we would be able to exactly compute the left hand side here, right? And then that would give you the TB or PQ.
Oh, oh, oh.
Uh,
So this is actually the reason this is complicated is suddenly, sorry,
Is
you're
it-
summing over points in the domain. So this is not at all small. This is a big
This is
beast.
not at all, yeah. So the point is that even for very simple classes of distributions like product distributions, where
Yeah,
P
yeah.
and Q are simply the product of these marginals, the optimal coupling distribution seems to be very hard to characterize.
Ah,
Um,
oh.
and we don't have like, a good way to make these computations of what is the probability of X not equal to Y for the optimal coupling distribution even between product distributions. And so that's why we resort to so that's the point I was trying to make, that instead of the optimal coupling, we now look at this local coupling, which
Mhm.
is a coupling between the marginals. So the local coupling, yeah, so the idea for product distributions is that somehow if, so I have P is basically a product of P1 through Pn, right? And Q is a product of Q1 through Qn.
And the whole, okay, yeah, sorry, but this is extremely helpful. Thank you for your patience. And
Yeah.
basically what you're saying now, P and Q have like immensely simple structure.
Right.
But now when you actually look at this proof construction that you did,
Right.
you're actually going to pick up like that description is going to scale
Yeah.
like the
So if I
size of the sample space rather than the size of this very concise description.
Exactly. So basically I can define this kind of simple coupling, which is the kind of, let me define it this way. So the optimal coupling between P1 and Q1 times the optimal coupling between P2 and Q2 up to the optimal coupling between Pn and Qn, right? But this is not optimal for P and Q in general. So it seems a hard problem to get a handle on the optimal coupling even for product distributions. But the idea was that, I mean, it could still be, because C is simpler to understand computationally. We can do computations on C, and it turns out that it's actually an n factor approximation. This probability of X not equal to Y under C is at most n times the probability under the optimal coupling of X not equal to 1.
And the point is, you expect these probabilities to be so small so that you're not too worried about this factor n?
No, so we are worried about the factor n, but it's still a polynomial factor, not an exponentially large factor.
Yeah, yeah.
And because this is now, so then you can get, and then the goal here is to estimate this ratio. The probability under the optimal coupling of X not equal to Y and the local coupling that X not equal to Y. So the denominator is actually easy to compute explicitly. So, and we know that this is at least 1 over n. So the point is that because you're trying to compute something which is not exponentially small, it's at least inverse polynomial, you can get a relative approximation of it using a polynomial number of samples. So like for example, if you're trying to compute like let's say the probability of some event happening which happens exponentially small, like the event of the probability of the event happening is exponentially small, right? Like then you need to make exponential number of samples in order to get like a relative approximation of it. But
So
because
just
we
as,
know
yes.
but because we
So,
know that this quantity is large, I mean, is at least inverse polynomial. An polynomial number of samples is enough to estimate it, to get a relative approximation of it.
So again, just to sort of rephrase what you already said, the point is that this quotient, which is just some number, right? Since this number is not too small, you're saying we can approximate this. And then you're saying that the denominator of this, we can actually nail exactly.
Yeah, because this C has this very nice product structure, and yeah, we can exactly compute, we can exactly do inference, and we can exactly
so
compute.
clearly now we're sort of saying, well, if I can approximate A divided by B very well, and I compute B exactly, then it sort of stands to reason that I'm
Yeah,
approximating A. That's basically what you're saying.
exactly.
Okay.
Yes.
Yes.
Yeah.
Makes perfect sense. Thank you so much.
But right. So then I mean, coming to I mean, our work, which is a bit more yeah, along these lines, but is yeah, involves some other ideas. So basically there so we don't actually so the C that we construct is not actually a coupling. So we only have on one side, so so this local partial coupling. So this is what we introduce in our work. Is that, I mean, basically our observation is that it's actually enough for you to only preserve the marginals on one side for the purposes of this proof to work. So you can get, so we only ensure that x1 to xn is sampled as in P, but y1 to yn may have different marginals. Okay. And kind of the meat, like the technical meat is showing this inequality that, I mean, so, okay, so we define some kind of this partial coupling, which only ensures one side consistency. And also we show again this ratio, the lower bound on the ratio. But this, but the
Even
proof
for
of
a
this
partial coupling.
even for a partial coupling, but this is where things get quite a bit more technical and complicated, and I didn't really describe it in the talk. So here again we show 1 over order 1 over n lower bound for this ratio.
And is it easy to understand why you want to get away with the partial coupling rather than constructing a full one? Like it would be hard for you to do it.
Maybe yeah, I mean, maybe let me just say why we cannot. I mean, why it seems hard to get like a full coupling. So if you remember, I mean, so here in for product distributions, what we had was that the coupling itself was a product, right? And the hope is that maybe if the coupling has the same structure as the distributions themselves, the individual distributions themselves, then what we can do is if you have an inference oracle for the original distribution, so meaning that you can compute, you'll be able to compute marginals on subsets of variables for the original distribution. Okay, maybe I'll say it another way. So for product distribution, we had the coupling itself be a product distribution, and we wanted product because product was simple, right? And so let's say now we have, so let's say now that we are looking at Markov chains or like a path graph. So we like the graph looks like this, right? And so this is a simple distribution, you could say. And yeah, let's try to get a coupling also, which has the same graphical structure. Okay, so the coupling also has the same, this kind of a structure. But now the coupling is on these pairs x comma y. So you have x1 comma y1, x2 comma y2, to xn comma y. Okay.
Mhm.
And maybe better way to think about it is that you have these pairs. Okay. And each one here could potentially depend on both and so on. So now the
Mhm.
point is that even if I have that, yeah, so in this chain, what I have is that, for example, x2 and x4 become independent of each other if I condition on x3, right?
Mhm.
Um, so now, but if I now have this path on pairs, right? And truly, actually, um, yeah, I mean, you have that, um, uh, yeah, I mean, x3 could depend on both x2 and y2. So then there's this issue, kind of a backdoor path switch comes up. So it could be that even if x4 and x3, um, so even if your x4 and x2 are independent condition on x3, there's now this new path which goes through y3,
Mhm. Yes.
which connects x2 and x4.
Mhm.
So it's not, so you cannot, I mean, yeah, so it's not true. So even if you have this kind of a structure, it's not true that x2 and x4 will necessarily be independent, conditioned on x3, right?
Mhm. Mhm.
So just because you have a path structure on the pairs does not ensure that you have a path structure on one side of the path, like just on
Mhm.
the axis, right?
Mhm.
So, and it seems difficult, yeah, if not impossible. I mean, okay, we haven't proved this formally, but informally, I mean, it seems almost impossible to have something which is a path structure on the pairs and also is a path structure on the marginals of x and the marginals of y separately,
Mhm.
which is what you need if you wanted, I mean, yeah, like the x to be a copy of a path and y also to be a copy of a path. So if you have, I mean, then it basically enforces so much structure that that I mean, you cannot get something which is close to being optimal.
Mhm.
It's kind of very high level intuition.
Yeah.
So
Yeah.
what
Yeah.
all, yeah, so right. I mean, so that's why we kind of give up on this idea that that both, I mean, these guys should form a path as well as these guys should form a path. So we can ensure that one of the two sides forms a path, but not both of them altogether. And
Mhm.
then, but we still have this structure that the pairs form a path.
Mhm.
Okay. Um, yeah, that's some very high level intuition. Sorry.
Yeah. Yeah. No, it sort of it makes some sense. Yes.
Yeah. Um, right. Um, yeah. So, yeah, I mean, so what we really do is basically we have this condition that for let's say for this coupling, so the probability that xi is equal to some, so xi and yi are equal to b conditioned on xi minus 1 equal to, I don't know, a1 and yi minus 1 equal to a2. This is the min of p of xi equal to b given xi minus 1 equal to a1 and p of Q of yi equal to b given yi minus 1 equal to a2. Okay. So this basically ensures it basically ensures that the conditional probability distributions are optimally coupled. Okay. But then also we need, but in order to also get that the xi's themselves are form a path. Okay, so I think I wrote this down earlier. Let me scroll to, but also, prime, the C of xi equal to b, yi equal to b prime, given whatever. Yeah, this is equal to p of xi equal to b conditional. So kind of we ensure both of these conditions. So the first condition ensures that you have a path on the pairs. And the second condition, because it's a path on the pairs, because the probability of xi comma yi only depends on the probability of xi or only depends on the values of xi minus 1 and yi minus 1. It doesn't depend on anything else, right? So you can write it as a path. But then the second condition also ensures that it's a path on first coordinate. Path on the axis. Because no matter what the previous what the previous values are for xi minus 1 and yi minus 1, if I look at the marginal on xi, it only depends on xi minus 1. It doesn't actually depend on yi minus 1. So this, we can actually construct, explicitly construct this kind of partial coupling, which ensures both of these are going on at the same time. And this is enough to drive our proof. So that's one part. And the other part is to ensure this inequality, that the ratio is at least inverse polynomial. And this is also a more involved argument than the argument for product distribution. So for product distribution, I think I mentioned that this lower bound is actually just a one-liner. It just follows from the ratio between max and the sum. But it seems, at least in our proof, that for general Bayes-Nets, that proof is quite a bit more involved. But we are still able to get order 1 over n for the ratio.
I see.
Yeah. Okay, so I guess I'll stop here.
Yes, thank you so much. This is extremely helpful. This is very enlightening. I learned tons, so thank you so much. Yeah, we've been forcing you to entertain us for long enough now, I think. But just, are there any final questions from anyone other than yours truly? Take your final chance now. Otherwise, we'll just say thank you again, Arnab, for an amazing talk. This was really, really nice.
Thank you.
Thank you so much.
Yeah, thank